Hello students and welcome back to our class. So today we will be discussing about the comparison tests for improper integrals having infinite range of integration. So these are quite similar to the improper comparison test for the improper integrals with finite range of integration. Okay, so let us have a look. The first one, if f and g are positive and fx is less than or equal to gx for every x in a infinity, then integration a to infinity fx dx converges if integration a to infinity gx dx converges. Okay, that is, if the larger one converges, then the smaller one will converge. And the second one, if integration a to infinity g dx diverges if integration a to infinity f dx diverges. Okay, that is, if the smaller one diverges, the larger one will diverge. Okay, so it's similar. Then the second comparison test, it is in the form of in the limiting form, and it's also quite useful. If f and g are positive in a infinity and limit x tends to infinity if fx by gx equal to L, where L is non-zero, then the two integrals a to infinity f dx and a to infinity g dx converge or diverge together. Okay, and if the limit is 0, then also we can draw a partial conclusion. And what is that? If L is 0, then if L equal to 0 and a to infinity g dx converges, then a to infinity f dx also converges. And if L is infinity, then integration a to infinity f dx diverges if a to infinity g dx diverges. So that we can apply. So let us have a look at this. Examine the convergence of a 1 to infinity dx by x root over x square plus 1. So mostly we will use the comparison integral as dx by x to the power n, and I had given you this as a homework, and yeah, I have solved it also in the last file that I have sent you. That yeah, did I solve? Maybe I have not solved. You can always solve it. It's quite simple. Integration dx by x to the power n converges if and only if n is strictly greater than 1. Okay, so we will use that integral for the comparison. So from here, in the numerator, in the denominator, you see the power of x that comes, the after simplification, the power of x that comes here is what? X square will come out as x. So x into x is x square. In the denominator, you will get the power of x is x square. So this gives us a rough idea that we can take the comparison integral as gx equal to 1 by x square. So we take gx equal to 1 by x square, and then we take the limit x tends to infinity fx by gx is this, and if you just simplify, it comes out to be 1, which is non-zero. So that means a to infinity 1 to infinity dx by x square and 1 to infinity dx by x to root over x square plus 1 converge or diverge together. Okay, but this one converges because the power of x here is 2, which is greater than 1. Okay, so the given integral is convergent. So you try this yourself. It's similar to the previous one. This also you can try. It's similar. Okay, the fourth one, say 0 to infinity e to the power of minus x square. Okay, so we test the convergence of 1 to infinity e to the power minus x square. Okay, so why we are doing that? Because for comparison, we will use integrals of this type, 1 by x to the power something. Okay, but here the range of integration includes 0 as well. Okay, so if we compare it within this particular range, 0 to infinity, then we will be in trouble, because dx by x square has got different interpretation for 0 to infinity. Okay, so from 1 to infinity, we know the result, x to the power n, it's convergent if n is greater than 1. But for 0 to 1, what was the result? If you remember, this converges when x is, the power is less than 1. Okay, so that will create a trouble. So in fact, we can test the convergence for 1 to infinity e to the power minus x square dx, and then come to conclusion, because 0 to 1 e to the power minus x square dx is a proper integral. Okay, so that's not a problem. Since it is a proper integral, 0 to 1, within 0 to 1 it's a proper integral, so we can just test the convergence of 1 to infinity. Okay, and if it is convergent, then the given integral is also convergent. So therefore, let limit x tends to infinity fx by gx is what? Limit x tends to infinity x square by e to the power x square, okay, and which is of the form infinity by infinity, and apply L'Hopital's rule. So we'll get it's 1 by e to the power x square, and its limit is 0. Okay, but integration 1 to infinity dx by x square converges because 2 is greater than 1. Hence, integration 1 to infinity e to the power minus x square dx also converges. Again, 0 to 1 e to the power minus x square, sorry, it's minus x square, please make this correction. 0 to 1 e to the power minus x square dx is a proper integral. Hence, this given integral can be written as the sum of these two, because the first one is a proper integral and the second one is a convergent integral. Okay, so the original integral also converges. Okay, so this one, fifth one, you can try it yourself. The sixth one, 0 to infinity sine squared x by x squared. So this is also something similar. 0 is included here, but we have x in the denominator. Okay, so we test the convergence of 1 to infinity of the same function. Okay, because 0 to 1 sine squared x by x squared is a proper integral. Okay, so if it were improper integral, then we have to test both. Okay, so here 0 to 1 sine squared x by x squared is a proper integral because sine x by x tends to 1 and x tends to 0. Okay, so we just need to check the convergence of 1 to infinity sine squared x by x squared. Take fx as this, and since sine squared x is there, it's very simple. We can apply the first form of the comparison test. So that is this less than or equal to 1 by x squared, but integration 1 to infinity dx by x squared converges. So by comparison test, integration 1 to infinity sine squared x by x squared dx also converges. Okay, and since the first 0 to 1 integral part is a proper integrals and this part is convergence, so the sum of these two is convergent. Okay, yeah, the seventh one, integration 0 to infinity x tan inverse x by 1 plus x to the power 4 whole to the power 1/3. Okay, so what we do, we just extract the power of x to the power we just extract the power of x. Okay, so we take x to the power 4 outside, it will come out as x to the power 4 by 3, and then if you simplify in the denominator, you will get x to the power 1/3. So you take gx equal to 1 by x to the power 1/3, and then take the ratio. The ratio comes out to be pi by 2. Okay, so therefore which is non-zero, so therefore 0 to infinity f dx and 0 to infinity g dx converge or diverge together. But integration 0 to infinity g dx diverges as 1 by 3 is less than 1, hence the given integral diverges. Okay, the next one is integration 0 to infinity x to the power m minus 1 into e to the power minus x dx. We have to show that it is convergent if and only if m is greater than 0. So this particular integral is called the gamma function, which we will do in the very next lecture. Okay, so there are two types of special functions which we will be doing: the beta function and gamma, which is also a part of our course. So there are some special properties of these functions. We will do that in the next. The integrand has infinite discontinuity at x equal to 0. So if you observe carefully, if m minus 1 is negative, in that case the integrand has infinite discontinuity at x equal to 0. So that means what? We have to separate two cases, right? So we consider the convergence of the two integrals 0 to 1 x to the power m minus 1 e to the power minus x dx, and 1 to infinity x to the power m minus 1 into e to the power minus x dx separately. Okay, so first let us see the convergence of I1 at 0. So fx is this, which can be written as e to the power minus x by x to the power 1 minus m, and we take gx as 1 by x to the power 1 minus m. So fx by gx is 1, which is non-zero, so they converge or diverge together. But 0 to 1 x to the power 1 minus m dx converges if and only if 1 minus m is strictly less than 1, that is m is strictly greater than 0. That means this first integral I1 converges if and only if m is greater than 0. Okay, next we have to see for what values of m the I2 converges. Okay, so let us write fx as x to the power m minus 1 into the power minus x, and we take gx as x square. Okay, 1 by x square. So fx by gx will be limit x tends to infinity x to the power m plus 1 by e to the power x. Okay, so there are several cases. If m plus 1 is negative, in that case this limit will be 0, because it's of the means it will be the x can be taken in the denominator, so it will be like 1 by infinity. Okay, so that will go to 0. So if x is less than or equal m plus 1 is less than or equal to 0, there is no problem, this limit is 0. Okay. If m plus 1 is strictly greater than 0, then it is of the form infinity by infinity, and we can apply L'Hopital's rule repeatedly. Okay, and after a finite number of steps, the power of x will become negative here, because if you take the steps up to this, that is the greatest integer of m plus 1 plus 1. Okay, up to that step if you take, then this the power of x will be negative. Okay, this will give the negative power of x, so that the limit in that case will be 0. Okay, and for m plus 1 less than or equal to 0, already I have explained why it's 0. So thus limit x tends to infinity fx by gx is equal to 0 for every m. Okay, whatever m you take, it's always convergent. Okay, but integration 0 to 1 x to the power m minus 1 e to the power minus x converges if and only if m greater than 0. This part converges for all m. Okay, so I have to take the common part. 0 to infinity x to the power m minus 1 e to the power minus x will dx will converge if and only if m is greater than 0. Okay, because for m less than 0, this one is not convergent, 0 to 1 part. Okay, for every value of m, 1 to infinity is convergent, but the other one is convergent only if m is greater than 0. So the given integral, original integral, converges if and only if m is greater than 0. Okay, otherwise it's not convergent. Okay, then there is a concept of absolute convergence. The improper integral a to infinity f dx is said to converge absolutely if a to infinity mod f dx is convergent. Okay, and we have a result that every absolutely convergent integral is convergent. Okay. Integration a to infinity f dx exists if a to infinity mod f dx exists. So if we can show that a given integral is absolutely convergent, we can conclude that it's convergent. Okay, so for example, the 1 to infinity x to the sin x by x to the power p converges if p is greater than 1. Okay, so sin x by x to the power p, it can be written as mod of fx is mod sin x by x to the power p, which is less than or equal to 1 by x to the power p for every x greater than or equal to 1. Okay, so this was the thing. Yeah, so I have but integration 1 to infinity 1 by x to the power p dx converges if p is greater than 1. Hence this integral converges if p is greater than 1. So 1 to infinity sin x by x to the power p also converges if p is greater than 1. Okay, this was the theory about comparison tests. Okay, so I have given a few homeworks. Please try those homeworks, and the next lecture we will be studying some important properties of beta and gamma functions. Thank you.